Okay, so now let's make a connection between 1D simple harmonic motion and two-dimensional circular motion. So what we're going to start off with is addressing a ball, let's say a mass moving in a horizontal circle. So we're going to define a couple things, that the radius of the circle is A, the angle that it makes in relation to where it can be at any point is theta, and then x describes the distance away from the center. Okay, we know that the velocity is always tangential. The maximum velocity is tangential to the circle. Okay, and we want to show that this also looks like a simple harmonic oscillator. Okay, so if we start off with just addressing that last concept, that if we look at the animation that we were playing with before, and we put our plots, what we see right here is that when this thing is going its fastest, if you just watch that circle, this pink circle, go across your screen, you see that it's moving fastest this way in the center. It slows down and then starts moving fastest back the other way. Another example that you can see of this, if you ever watched an object that is rotating in a microwave, and if you just look at it from the front view, what you see is that it's going around and it's moving essentially left to right. And when it does so, it acts as if it is moving in like a simple harmonic oscillator. If you forget the fact that there is some depth, if you just look at the one-dimensional version of a coffee cup in the microwave, it's just oscillating back and forth. And it stops at the side, at the extremes, and it's moving the fastest in the middle. So let's do some math here. That we have an amplitude A is our radius, so that stays the same. We can also break up this Vmax into a velocity V and an angle theta. Okay, and these two thetas are the same because this is perpendicular. The A and the Vmax are perpendicular. So if this is theta, then the angle over here is theta by alternate interior angles. And then if this is theta and this is 90, this one is going to be 90 minus theta. So that's just kind of a little proof that this angle and that angle are the same. And of course, based on Pythagorean theorem, that if this is one leg and that's another leg, we can write this as the hypotenuse squared minus the other leg squared. So basically just a squared plus b squared equals c squared. And so let's write this out. So if we describe sine of the angle equaling v over vmax, so that's definition just of sine, so vmax. And then sine of the angle also equals radical a squared minus x squared all over a. And since these angles are the same, what we essentially have is two equations equal to the same quantity. We could set them equal to each other. So we have v over vmax equaling the square root of a squared minus x squared all over a. And I'm going to rearrange this and solve for v. So I have v equals, so cross multiply by vmax. And I'm going to write it like this. So we have vmax over a times the square root of a squared minus x squared. And the reason I wrote it like this is because essentially I want to put this a back in the square root. Okay, so by doing so, I can put, so this is vmax, I could square it and put it in the denominator. So I'm going to square it. So I have a squared minus x squared all over a squared. And when I do it that way, what I end up getting, this is 1. So this is the square root of 1. And then I get minus x squared over a squared. And what do you know? We have our simple harmonic oscillator equation. So this is kind of a little proof that an object going around in a circle is essentially a simple harmonic oscillator. So if we watch this object, as I mentioned, like the coffee cup from the side, what we'd see is this thing is oscillating back and forth, going the fastest in the middle. And if we want to describe that speed, we know that the speed of something going in a circle is the circumference divided by the radius, divided by the period. So if the radius is a, then we have 2 pi a over the period. And if I essentially rearrange this, okay, for the period, I get period equals 2 pi a over v, and since this is the velocity at which it's traveling at, this is the maximum speed. And we saw from the previous page that the maximum speed is a times k over m. So this is from the previous page. We did v max a times radical k over m. So the a's cancel out, and so I'm left with 2 pi. And what I'm going to do is I'm going to actually copy, change, flip this. This is 1 over radical k over m, and that reduces to radical m over k. And this is the equation for the period of a spring mass system. Okay, it's the mass divided by the spring constant, the square root of that, and multiplied by 2 pi. So, in these examples, I got for the period, and once again, as before, work these out and see if you can figure them out, but I got a period of a half a second, and I also got a spring constant of a 0.19 newtons per meter. Okay, so small value. And the period will go up by a factor of radical 2, and the frequency would then go down. So the frequency would go down by a factor of radical 2. And you can kind of make that connection here, that once you know what happens to the period and frequency are inversely related. Okay, so now we're trying to show that a pendulum is a simple harmonic oscillator. Okay, so essentially if we can figure out that the restoring force, okay, so F sub r, which we'll go through the force diagram, but it's going to work out to be the parallel weight. If we can show that that is proportional to x, okay, much like that the force on a spring is proportional to x, then we can kind of conclude that the pendulum is a simple harmonic oscillator. Okay, so let's draw some free body diagram here. So we have the tension force going up. We have the force of gravity, or the weight, going down. And we can break that weight up into the perpendicular component, which is the mg cosine theta. And then we could also break it up into the parallel component, which is the mg sine theta. And if we have an angle here of theta, then the distance away from that equilibrium position, we'll call that x. And let's call the length of the string length L. Okay, so the length of the string is L. So you can see that if we just work with distances, the L's and the X's, we can say that sine of theta is equal to L over X. So that means that my X is equal, if I solve for X here, X is equal so excuse me, that sine theta is actually equal to x over L. So if we say that the restoring force, which is mg sine theta, we see that we can substitute sine of theta in for really mg x over L, and what we end up seeing is that the restoring force, okay, so therefore the restoring force, F sub r, is proportional to x. So what we end up getting is a simple harmonic oscillator, and our kind of substitute k in here, so the analog for k in this case is mg over L. Okay, so I'll put that in quotations, that the k is mg over L. So if we go back to the previous equation, that the period of a mass spring system is 2 pi m over k, and we substitute in our analog for k, what we end up getting is that we have 2 pi times m over mg over, L, and the m's cancel out, and we copy, change, flip this. What we end up getting is 2 pi radical L over G. And so this is the equation for the period of the pendulum. If you kind of go back to our period of the pendulum lab, what you ended up seeing is that the only factor, the only variable that changes the period of the pendulum is the length of the spring. So we see the mass is independent and we don't see any angles. So those are the three variables we tested. Okay, so this is the period of the pendulum. And you can find this in your reference tables. Okay, so the last thing that we want to do is take a look at modeling simple harmonic motion as a function of time. So what we want to say is what is happening to its position, velocity, and acceleration as a function of time. Okay, so you guys have done this in your math class, that we want to say x as a function of t. So basically what we want to look at is that if we describe, and remember that this is a here, so if we describe between the relationship between x and a, we have a cosine function. So I'm going to write out the cosine function. So x is, so if we have cosine of theta equaling x over a, then x is equal to a cosine theta. But then now the question is, what is theta? Well, theta, if you remember, is our angular displacement. Okay, and angular displacement is equal to the angular velocity times time. And this, we're kind of making the assumption that this is constant. And basically this is a rewrite of, we know v bar equals delta x over t. So we know omega bar is equal to delta theta over t. So essentially what we're doing is solving for theta. And omega, if you recall from our rotational motion, is the angular velocity. And we wrote it, we actually solved it for 2 pi f. And so really we have angular velocity, but this, in this case of something going around in a circle, what we actually typically call is it's angular frequency. Okay, and we'll talk more about the differences between the two, but for our purposes right now, they are essentially the same. And I could also write this as 2 pi, since frequency and period are inversely related, over t. So essentially this becomes a times cosine. I'm going to substitute omega t in for that, and then also substitute omega as 2 pi over t. So I get 2 pi over t, that's my period, times t. Okay, and so this is my position as a function of time for any time t. Okay, and a and is the amplitude, so that's the radius of the circle, and t is the period for how long it takes to go around one complete revolution. Now the velocity is going to be equal, so kind of similar argument here, that we have a circle, we got a theta, that it's actually going to be a sine. So what we end up getting is velocity as a function of time is equal to the Vmax times sine of theta. And we can make a similar substitution. Actually, I'm going to throw a negative sign in here because it's going to the left and we made our x positive. So we have Vmax times sine, and I'm going to substitute omega in for this. This is 2 pi over period times t. And then that negative stays there too. And so before I run out of time here, I'm just going to write down what the acceleration vector is. The acceleration vector is also negative because it's accelerating that way to pick up speed. And so acceleration, if you recall, well, here, minus k over m a cosine of 2